That's the way I got along in life. I don't ever remember being particularly jealous of anybody, because I figured if I can't do it myself, I don't deserve to get it.
The Interplanetary Podcast. The exploration of space for the benefit of all humankind. Your hosts are Devin and Guilford, George and Matthew Russell.
Oh yeah, baby, Clyde Tombaugh. It's his birthday today, or would have been his birthday.
Had he not have died.
Had he not have died. Do you know what Clyde Tombaugh is famous for?
Is it discovering Pluto?
He's discovering Pluto. Amongst other things, he's also quite famous, as Lynn and I discussed, he was also quite famous in terms of pushing for the research of unidentified flying objects in our UFO special, I seem to remember. Yeah. So, unfortunately, I don't think he ever lived to see his planet demoted to...
Yeah, he died in
to a dwarf
97.
planet. Yeah, so yes, he died in 1997, and Pluto became a dwarf planet in 2006.
By our boy deGrasse.
Yeah, I wonder if he got a heads up though. Look at that, he lived to almost. He would have been 100. That's a bit annoying, isn't it? He would have been 100 years old. Just it would have been a terrible 100th birthday present. That one.
Happy birthday! You're no longer as special as you thought you were.
Yeah, but he did live to quite a ripe old age. He died at 90. Not bad. Born in Illinois.
Terrible for a turtle, though.
Is it?
Or a tree.
Yeah, February the 4th, 1906, Illinois. Died in New Mexico in 1997. Amazing, isn't it, that the discoverer of Pluto died in 97?
Yeah, it just goes to show how we don't know anything. We're barely scratching the surface.
Yeah, the discoverer of Pluto died after Freddie Mercury.
It's crazy.
There is some weird connection
It's
there.
weird that the discoverer of the quadratic equation died before Jesus.
yeah, there was a lot of maths, and
Maths was the early, but then it seems like physics is
everyone has just been
a bit late.
Playing catch up ever since. George, welcome to the podcast yet again, helping me out here. The very first little story I wanted to talk about is not one that we've sort of gone over, is it? But I really wanted to talk about this star formation near the sun is driven by expansion of the local bubble. So this is a paper that was published quite recently in Nature, 12th of January, 2022, by Catherine Zucker et al.
She related to Zuckerberg?
No, I don't think so. Don't think names work like that, George.
Really?
Yeah. So have you ever heard of the local bubble?
I have not heard of the local bubble until now.
Well, the very start of the abstract of this paper will belittle you, because it says, for decades we've known that the sun lies within the local bubble. We. But anyway, we do, George.
Us scholars, fellow scholars.
Us fellow scholars. A cavity of low-density, high-temperature plasma surrounded by a shell of cold, neutral gas and dust. In other words, there's this expanding bubble. Now, the sun actually is travelling through this local bubble. So the bubble is in the Milky Way, and it's this sort of, like a bubble, like a bubble. And
a sphere with very thin...
Well, it's actually, it's not really a sphere. It's more peanut-shaped, which is quite cool, isn't it? Gaia, the space telescope, as you know, is very, very good at mapping how far away stars are and how much they're moving. So it's been able to accurately get their position just right and map it loads and loads and loads and loads. It's been working out the movement of the stars. So it's been able to map what exactly is going on. And from this data, one of the really surprising things, that's surprising to me, is that all the young stars that are formed within 500 light years of the sun, all of them happen at the edge of this bubble.
Doesn't surprise me.
Doesn't that surprise you?
Intuitive.
So as this plasma bubble is going out into the Milky Way, it bashes into the interstellar medium, and that is where these shock waves are sort of making stellar nursery clouds collapse.
What is the interstellar medium? Is it just the space in which?
Well, yeah, it's just it's
just
the space between the stars. It's interstellar. It's the stuff in between stars. And the stuff in between stars is different within this bubble. Hence, it's a bubble. The bubble.
What kind of things make it different to if we were outside?
It's less dense and hotter. It's been caused by a supernovae, about 14 million years ago, I believe. So that was, a lot, maybe several supernovae, but the supernova happening at the center of this bubble, the center where the center would be now, and it's created this giant bubble that's forever expanding out, and it's still expanding 14 million years later.
Our solar system's kind of in the eye of a storm.
Kind of, yeah. It's more like in the eye of a big burp into space.
Big explode. It's like if there's something exploded, then you teleported into the middle of that explosion.
Yeah, like millions of years later, where it's still a little bit warm, but the explosion's still happening. It's still expanding out into the galaxy.
So there's kind of like front of this explosion that's like really hot, and it's just going through decimating things.
Yeah, well, not decimating thing. It's doing the opposite. It's giving birth to stars. It's pushing the interstellar medium together, and all the star formation is happening on the edge of this bubble.
But if any planet were to be, already there.
No, I don't know, because we're in it.
Yeah, but we're behind it. But I mean, like, if there was a planet.
No, I think it's all the same. Like the bubble is made from the same. Like the actual outer edge of the bubble, I don't think is any different from.
Right, so it's like when two fronts of air with different temperatures meet, they create hurricanes.
Exactly, or rain. So it's very much like weather front. Yeah, so it's a weather front, just like a weather.
So it's a
weather
space
front.
interstellar weather front.
Well, exactly. It's a galactic weather front.
Right.
Where and it causes starbirth. How cool is that?
That is really cool.
That's a very cool little story.
What's the paper's name?
The paper is Star Formation Near the Sun is Driven by Expansion of the Local Bubble. Does what it says on the tin. It is a cuprinal paper.
Yeah, fellow scholars better check that one out.
Yeah. There's lots of write-up in various places, like the Wall Street Journal, if you can get past their paywall. I thought we'd talk a little bit about the James Webb Telescope. And the question that we were asking right at the beginning, because it's now reached there, is how do you orbit the Lagrange point?
It's a very hard question.
I feel I'm pretty glad that I looked at it, because it kind of makes a lot more sense in my head now that we had a quick...
Well, you're glad that you researched the podcast instead of just randomly making...
No, I'm glad. But the best thing about doing the podcast is when you research it, you learn something, and that's
true.
So when you try and talk about...
Yeah, the best way to learn is to teach.
Oh, that's exactly right. I don't think of myself as teaching, more communicating.
Being a part of the community.
Yeah, being part of, I'm part of the space community.
Yeah, exactly.
Like a spokesman for the science itself. So the second Lagrange point, L2, very, very popular. And why is it popular, George?
Well, it's a quite stable point for any kind of spacecraft that wants to be at any given Lagrange point.
Yes, it's a parking place, really. It's a stable point.
It's like a really cheap parking spot.
It is, but it's really good, L2, because the Earth, the moon, and the sun, which, as you know, are the three brightest objects in the night sky, particularly the sun, is very bright. The moon's very bright as well. And if you're off the Earth is very bright as well, and you're nearby. So the reason why L2 is great is because all of them can be behind you while you look out into space, right? Agree?
So you're shielded from all. It's the same selling point for having a telescope on the dark side of the moon, where you're shielded from noise from Earth.
Well, yeah, and light from Earth and everything from Earth.
Noise from the sun.
So the whole point about the James Webb Telescope, of course, is it's got this ridiculous heat shield. It's got this shield that it sits on, this amazing piece of technology that made it very expensive. And so one side is extremely cold as well. The other thing about Lagrange point out there, it's very cold, but it's pretty stable in temperature. So that the one side of the heat shield, the sun shield, you're super cold. The other side, you can still communicate with Earth. Now, the other genius thing about the L2 point is that you can get into a halo orbit around it. And so you can always see the Earth, so that you can always send your messages to and from the Earth. And you can always see the sun with the hot end of your spacecraft, so that you can power your spacecraft.
So you get kind of the best of both worlds.
You get the best of both worlds. L2, really, really cool.
Right? What's the camp called for L2? The asteroid camp, because they all have names, don't they?
They do, but remember that only happens at L4 and L5 because they are more stable. So you don't get Trojan asteroids at L2 and L1.
So L2's
points.
not that stable then.
It's not stable enough
for asteroids.
Yeah, but and one of the reasons is
campers.
Yeah. And the stability thing is a little bit oversold, because even L4 and L5 aren't completely stable.
Yeah, you're dealing with chaotic systems, because
it's
three
still
bodies.
Yeah.
Or more than three
it
bodies.
It just so happens that if you think about it as energy, if you think about it as gravity wells in a dome, in a sort of, if you've got one great big dome and you're on the outside and you think of gravity wells caused by the planets, the saddle points are the Lagrange points. Well, regardless of L4 and L5 being a saddle point, they're still unstable to a point. There will be a point where if you drift slightly off it, you're doomed, right? Now, a Lagrange point, the thing that I think people get a bit confused is that they think Lagrange point is where the gravity sort of equals out, where it kind of, the pull of the Earth equals out the pull of the sun.
Yeah, so the distances are such that relative gravity for the sun, so equals to the.
But that's not right, of course.
It's a little bit. It's sort of. It's an approximation. It's close.
I think it's good enough for that sort of for your man in the street, but not for an interplanetary podcast.
Yeah, so I always thought this, why is it points if it is just that? Because if it was just that, you would expect it to be like a line, like a Lagrange line.
Yeah, and what it's actually more to do with is what you're trying to do is balance out the centrifugal force, this fictional force.
Well, you're regarding all forces. So you're regarding the Earth's gravity, the sun's gravity, centrifugal force, the moon's gravity. You're balancing out all of these forces.
Yeah, and so what you're trying to do is what you want is the James Webb Telescope to follow Earth around in its orbit. But and I know that if you're in an orbit that's further out, then you must be going slower to stay in orbit. You'd have to be going slower, and so you'd start drifting away. So Mercury goes around very, very quickly. Uranus takes a very long time, and Pluto, I think, has only done one orbit since it was discovered. Right, so it's crazy. So how do you balance that out? Well, you balance it out because the gravity from the Earth and the Sun is exactly right at the Lagrange point to add. So the Earth's gravity added onto the Sun's gravity is exactly right to keep the James Webb Telescope going with the Earth around in orbit. That's one way of seeing it. Now, the really good thing about the halo orbit now is, why don't you just stick it on Lagrange point? The most amazing thing about the Lagrange point is the James Webb Telescope never gets closer than 250,000 kilometers away from it.
Yeah, because when I first heard, I was discussing the James Webb Telescope and Lagrange points with my physics teacher, and he said that it was orbiting the point, and I assumed maybe it's it's just a small drift from the point, but I assume that anything at the Lagrange point would be at a specific point, but it's literally orbiting nothing, like a blank spot.
Well, it's not orbiting. See, this is, I think, it only looks like it's orbiting from Earth. In other words, it's your frame of reference. So if you're standing on Earth, you would look out and see the James Webb Telescope orbiting around a nothing, right? And its orbit, by the way, is actually very elliptical. So it at its nearest point, it's 250,000 kilometers away from L2, and its furthest point, it's 832,000 kilometers
from the Lagrange.
From the Lagrange point, yeah. So it's nowhere near.
Yeah, Lagrange points. I guess it's really hard. It's so similar, unsimilar to what it not similar to what you'd think based on like the kind of man on the street kind of.
So what you got to think about at the halo point is that you're sort of wandering around the top of a mountain. So say the top of the mountain has been sort of slightly smoothed out. It's, in other words, it's a kind of a mound, and you're kind of moving around that mound where it's in perpendicular to the earth. And in this oval shape, and you're moving around that mound, and the local forces are just enough that it keeps you on top of the mountain. So all these perturbations from the sun, the earth, and the moon are keeping you on that top of the mountain, and you occasionally need the odd thruster fire to keep you there. Now, there's not much fuel on the James Webb Telescope, and that's why that fantastic insertion burn by Ariane 5 to get it there exactly right. So it's going at exactly the right speed to do this thing. So if you look at it, so don't think of it as orbiting, as in going in a circle around this point. It only looks like that from Earth, in the same way that Mars
retrogrades. I was going to say this.
It does a retrograde.
It's like they thought originally that Mars was going backwards, but obviously it isn't. It just appears that it's going backwards. Yeah. It's not actually going retrograde.
So if you were looking at Mars and it was trailing a ribbon behind it, it would look like it did a circle occasionally, and that's exactly what the James Webb Telescope is doing. It's all that's happening is as it's getting perturbed by at the top of this crest of this little pocket of weird gravity, where the Earth, the Sun, and everything is interacting in such a way to compensate for this extra bit of centrifugal force. It slows up and speeds up, but it's going up. So if you zoomed out of the solar system, you would see James Webb Telescope sort of climbing up and going down and climbing up and going down, but you would still just see it going in a sort of like snaking its way around the orbit. So the Earth is going round in this kind of in an orbit, but it's doing it in a straight line around, whereas James Webb is kind of snaking up and down this thing, slowing up and speeding up as it does so that it stays in line. So obviously, as it's going up, it's got to speed up again to stay in line with the Earth, and that's what it's doing. It's not orbiting, going round anything. It's still going in a straight line. It's just speeding up and slowing down and going up and down in a kind of like it's on a wave. But
another like an unintuitive thing is you would think that a point like this would be kind of like trying to balance a pencil, where any slight deviation and you've gone too close to, let's say, the Earth, and so the Earth starts pulling you more, which brings you further from the point, and then as you get further, the gravity from Earth becomes more, and you go even further still. Kind of like, like trying to put a ball on the top of a sharp point. If it starts even rolling slightly off of that point, it's going to completely go down. But it isn't the case. In fact, you can be hundreds of, like tens of thousands of kilometers from the point, and still be perfectly within. You don't need any thrusters to get back.
Yeah, I mean, that's the problem with those diagrams of energy wells in rubber sheets, is they're only two-dimensional. They're not three-dimensional.
Yeah, you need to realise that the rubber sheet is real
only
life.
An analogy.
Well, it's actually like sheets. Rubber sheets are 2D objects which distort in 3D. Where in reality, you're dealing with a 3D object which distorts in 4D.
Yeah,
but that's hard. You can't visualize that.
Yeah, well, like
imagine a lattice, like a.
I mean, they've done. I mean, you occasionally see the odd artist that's tried to display.
Yeah, but it's still just warping in 3D. It's not. You can't possibly visualize.
No,
4D.
It's very hard. It's very hard. Do you know what the first ever spacecraft was to go out to L2?
Is it a trick question? Is it?
No, there is no trick question.
Is it James?
You either know it or you don't.
Is it the James Webb?
No. Because Gaia, which we've just talked about, the Gaia Space Telescope that's measuring lots and lots of stars, that's out at L2 as well.
Oh, right, okay.
In fact, there's a couple of ESA spacecraft out there already. So you've got Gaia, and you've got the Russian-German astrophysical observatory called Spectre RG out there as well. But ESA also sent the Herschel Space Observatory out there as well. But the very first one that went out there is the Wilkinson Microwave Anisotropy Probe, which, as you know, is very famous for taking that picture of the background microwave.
That kind of like oval shape.
The oval, yes.
The oval shape green.
The Molida map of the oval shape.
Heat map of the universe.
Yes, as in the moment of reionization. It's the earliest picture of the light of the universe, which is incredible. So obviously it needed to go out to L2 to get into that cool bit of space so that it could pick up that faint signal of heat. So that's why it's such a good place to go. And the Chinese sent that little satellite out to L2 so that it could talk to what?
The Chang'e one?
Chang'e 5, which is the little rover that's on the far side of the moon.
Is that the only rover on the far side?
Yes, it's the only object that's ever soft landed on the far side of the moon.
Have been litho braking methods.
There's been some litho braking.
But that's for testing the actual what the moon's made of. If you want to work out what a planet's made of, you put one probe on one side, on the other side you hit it with like basically a missile, and then based on the vibrations you can work out the
you can see
composition.
that it's not hollow and it's not a spacecraft.
That's what they want you to think.
Yes, I know that's what they want you to think. So that's L2. I feel as though I've got it's slightly better in my head now about Lagrange points.
If the moon isn't a spacecraft, then how does it move around?
It's a really good point. Maybe it's not moving. It's just
maybe Earth's moving around it.
No, it's there's a rotating frame of reference that's where the moon is still and everything else is moving.
I don't think rotation is relative though. Unlike
I have
motion.
no idea. So get this, James Webb Telescope. How many months do you think it will take to cool down?
6.
4 months. So it's not going to do any science until June. Even when it gets there, when it's ready to go, it's all unpacked. It's got to cool down, and it's got to cool down to something absolutely insane. It's got to cool down.
1 Kelvin?
No, it's a little bit higher than that.
2 Kelvin?
40 degrees above absolute zero, so 40 Kelvin. So minus 233 degrees centigrade. And of course, it's got to get that down because it's looking for heat. That is what its instrument picks up, infrared. Almost certainly, the moment it's switched on, see the most distant galaxy ever recorded, like in its first few moments.
Yeah, I mean, how much better is this than Hubble?
It's at least 10 or 100 times more powerful.
At least?
Yeah.
100 times more powerful.
Yeah. Well, that's why it's so expensive. So one thing that's really, really good is to look at the management technique that was absolutely slated by the 2010 report into the management of the James Webb Telescope, where essentially they underestimated the price and then continued to stick their head in the sand every time everyone was saying, this is massively running over budget. And it was like, yeah, don't worry about it. Let's just keep asking for more money. And it's like, they should have just said, like, this original estimate was just total garbage. But the sort of money spent on the spacecraft and the fact that it has deployed, I mean, it's risky as hell.
It was 100 times cheaper than F-35 or something. So,
well, yeah, but it's one object with one single point of failure, whereas the F-35 program, I guess, is a range of objects.
Killing machines.
Of killing machines or protection machines. You could see
peacekeeping machines.
Peacekeeping machines, yeah. I mean, that's the thing, isn't it? You wouldn't want your country without a military.
That is a good point.
When there's bad guys out there, George, there's bad guys.
Yeah, the only thing that can stop a bad guy with an F-35 is a good guy with an F-35
with better weaponry on it.
Yeah, and a nuke.
So so we've got more spacecraft joining James Webb. In ESA are sending out Plato and Ariel out there. And you've got the Nancy Grace Roman Space Telescope that is planning to go out there in 2027. So it's going to get a bit crowded, but apparently not. If you think at how big those orbits are, that the orbits are bigger than the orbits out to the moon around that Lagrange point. So there's plenty of space out there. Space is massive, George.
Say that again. So the distance from the Earth to the moon is smaller than the distance from the James Webb to the Lagrange point.
Yeah.
That is insane.
Yeah.
I always imagined it as like a centimeter orbit or something.
Yeah.
Like just like a bit of wobble.
A bit of wobble, yeah, but it's not.
It's like about as much
like
as a
that.
Wobble. It would be more accurate to say that the moon orbiting the Earth is a wobble.
Yeah.
Than to say, yeah, that's kind of there's a lot of space out there, even in the Earth Moon system.
Yeah, there's a lot of space out there. Now, talking of space, George, another paper that's come out, which is quite exciting, is about how astronomers are closing in on the detection of a new type of gravitational wave. Or actually a new way of detecting them.
This is like a new force.
Well, no, it's basically they've always theorized that there's so many of these black holes in the universe. There's lots and lots of massive, supermassive black holes, right? So all the kind of black holes that we've seen so far are all these kind of gravitational wave events have either been neutron stars, black holes, and that's it. So smallish black holes and neutron stars and pulsars. So what happens is, they get into orbit around each other and they whiz very, very fast and create these very fast ripples, like chucking a rock into a pond, right? There's something very, very fast. So it's like throwing a small pebble into a lake. Now, so LIGO and things like that are really well suited to picking up those types of ripples. So we're starting to detect those gravitational waves. But what they want to do is use the timing of pulsars. So say you've got say you're looking out and you see pulsars and they're a bit like buoys or buoys, as the Americans might call them.
Or as it's spelt.
Or as it's spelled, yes. I'm sorry, Americans, that's our fault. So the buoys out imagine them out in the ocean. You can see them bobbing up and down, and from that, if the ocean was completely black, it was pitch black, but each of the buoys had a little light on them, maybe you could work out roughly how big the waves were around you and what was happening, right? But you would need more than one of them because as you were going up and down over one wave, you're going up and down a different wave to the one that the buoy's going over. And you might have other waves coming across.
So you have to take into account your own bouncing.
Yes. So not only do you have to get this, so for this measurement to work, so what they're trying to do is find these very long ripples that may last years, weeks, months, years of a big ripple that goes through. And this is caused by supermassive black holes, like at the center of galaxies, orbiting one another.
Does it use like Fourier transforms and stuff?
Well, yes. I mean, imagine the Fourier transform definitely comes into some of the equations to try and get rid of the noise. Yeah.
How much of what we've talked about has been 18th century, like 17th century maths and stuff.
Oh yeah,
like Euler and Lagrange are both from the 1800s.
Yeah. Euler, Lagrange, Fourier, Newton.
Yeah, we had to have mentioned those.
Yeah, Newton, Fourier, Lagrange, and I mean, yes. Talk about absolutely.
Like, was it Euler who first discovered Lagrange points?
Yeah, so Euler discovered L1, L2, and L3, and Lagrange discovered the two stable L4s and L5s.
I think people kind of look over Euler a bit because, like,
yeah, but he does have a pretty important symbol, like
well, he's E.
Yeah,
he also could discover. He discovered sums E.
sums. Yeah, but okay, moving on from Euler because he is an absolute Jew. So you've got these enormous waves caused by gigantic black holes orbiting one another, and so in other words, there's this kind of ripple that's permanently going on, and this can move the Earth meters, right? These enormous ripples, but to be able to measure this accurately enough, you have to know the center of the solar system, as in the center of mass of the solar system.
It's called the Barry center.
The Barry center of the whole solar system, to an accuracy of like 100 miles or something.
It was 100 meters.
100 meters. Oh my god! So it's absolutely absurd how ridiculously accurate that has to be.
Yeah. Within to be able 9 Usain Bolt seconds.
There's this group called the International Pulsar Timing Array, the IPTA, and it's a collaboration of lots and lots of different places where they're trying to use all the data collected on pulsars. So just to recap, pulsars are just these beacons that are so repetitive. You can use, just like we used quartz in digital watches because of the way that they vibrate under an electrical signal, you can use pulsars as little clocks because they're so stable and so accurate. You can measure the timing of them very, very accurately. But of course, if the space in between you and that pulsar is being stretched, then the timing changes ever so slightly. So you can measure that little change. But there's lots of other things that you need to get rid of. Noise, like things getting in the way, like electrons getting in the way and stuff like that could be affecting the signal. And of course, other gravitational events. Can be other, the water's very choppy between us and all the pulsars, and you're trying to look for these much longer waves. So you're trying to get rid of all the noise. Now, the really exciting thing is what you'd expect if there wasn't any of this kind of stuff is white noise being really equal across all the entire spectrum.
Pure randomness.
Yeah, pure randomness in a way, yeah. And but what they have discovered is that they've found that they've got this background noise that's actually red. So it's actually a red noise that's going on.
How is red noise defined?
Well, there will be a sort of component of it, I guess, at one end of the spectrum that's noisier than at the other end of the spectrum. In other words, there's a signal in there,
some bias.
Yeah,
because I've always wondered what like the colors of the noises are, because I have a synth that has pink noise.
Well, pink noise is equal energy per octave rather than equal energy per frequency. So that's why it goes and pink noise goes shh. White noise goes shh and pink noise goes because it's giving as much energy between 200 and 400 as it is between 2000 and 4000.
So it's kind of logarithmically.
Yes, logarithmic. It's changing logarithmically.
And is that called pink just arbitrarily, or is it?
Yeah, I think so. Well, I guess I wonder if light has, because there's lots of different noises as well. Famously, of course, there's the brown noise. Do you know what that is?
Is that 15 hertz?
Yeah,
that makes you poo yourself.
Makes you go for a poo. Yeah, which they decided not to use in war because it's such a low frequency you can't direct it. So everyone shits themselves.
Sure, you can direct sound, right? Oh
no, not low. Not low frequencies. The lower
want to have a bomb
like
a mortar that launches a really big speaker over to the.
You're never going to let me finish this story.
Go on.
So anyway, we as these gravity waves get further and further apart, from milliseconds to hours to years to millions of years, you have to use different ways of measuring it. So milliseconds, obviously, you can use that using ground-based interferometers like LIGO. Obviously. So which they have been doing, right? Now the next thing is to get binary supermassive black hole mergers, and we'll only be able to do things like that when we start having space-based interferometers, which ESA actually sent up their test one at the beginning of the podcast, is something that we covered. LISA Pathfinder was sent. So LISA will hopefully be a space-based laser where you have these very, very long arms. But in space, you can have them really long and fire lasers, and therefore it'll be more accurate, and you can see things coming in. And again, you can cool them to much so your instruments are better. Now they will measure. They'll be able to measure binary supermassive black hole mergers that last hours. Then, using pulsar timing techniques, you should be able to see gravitational waves that last for years. That the frequency is years. The crest of one wave is a year behind the crest of the previous wave. So that's the periodicity of the wave itself. And millions of years you can see in the cosmic microwave background. So WMAP has kind of already seen. Interesting her. But yeah, so this is the first time they've seen this red noise signal. They're not calling it a slam dunk. There's loads and loads of stuff they have to do to rule out other noises that have caused it, other reasons why you have this signal. It could be that there's something odd in the way that pulsars spin down, for example. The fact that they've seen it means that it hasn't been ruled out. If they didn't see it with the amount of data that they've got, it would mean that they were barking up the wrong tree.
Could it not be like some kind of systematic error in the measuring?
Well, it could be, yeah. So they're not. So no one's getting a Nobel Prize just yet, but they think in the paper that there's enough data now to be able to nail it down and say, yeah, we found this. So they think the data's already been collected. It's just now the number crunching and the supercomputer time and the physics and the maths, et cetera, to just get it to that point where they can say, do you know what? This is a signal that we're seeing of very large supermassive black holes with undulating year-long waves that are going through us all the time.
So it's like another level.
Yeah, it's a bit like, imagine the wind are like pulsars collapsing, and they're creating ripples on the surface of the swell. So you've got this swell. You've got this. So the big swell is the year-long,
the main
supermassive,
swell.
yeah.
Like the tide.
Yeah.
And then, no, not the tides. Like the year-long.
Yeah. Well, just the swell of the.
Yeah. And then you've got the
swell
tides
in the ocean.
Is the next one along.
And then you've got the wind blowing ripples of waves over the top of that. So it's complicated.
Yeah, you've got like levels of
waves,
different frequencies of waves, and we've discovered the lowest one.
Yeah. So that we're trying. That's what they're trying to crack, and it looks like they're getting there. So,
is there any reason to think that it would go all the way down? Like there's just an infinite number of frequencies?
No, because obviously once you get down to the cosmic microwave background, that's it. That's the beginning of the universe.
But I mean in the other direction of really slow frequency. So like there might be 1/2 of the frequency that
sub-millimeter gravitational waves.
Yeah.
Very high frequency, not very low. Yeah.
That's what I meant.
Super high frequency. Well, I don't see why not. Yeah, I mean, I guess if you've got two tiny black holes, like proton-sized black holes, spinning around each other, they must be generating gravitational waves.
What note is the universe then?
What note?
Yeah. What if it's like?
Yeah, that's true. There might be a little note.
If they're all like multiples of each other.
Well, there's the lowest note that's been photographed, isn't there? Where there's been a black hole explosion and it's worked its way through the dust. No, it is something like F sharp minus 27 octaves below middle C.
I just made up F sharp.
No, it is. I think it is F sharp. It's something ridiculous, but there is the lowest.
It's one of the notes. It's one of the 12.
It's one of the notes, but it's 27 octaves.
Yeah,
below
I've heard it is very below middle C.
Yeah. Anyway, George, thank you very much for joining me on the podcast again.
It's been a pleasure.
I've really enjoyed looking at this week's science. Should do it more often, shouldn't we?
Yeah, like once a week or something.
Yeah, let's do it once a week. Right, that's it. Shall we say bye-bye to this podcast?
Yeah. Let's do it.
Let's do it. Bye!
Bye, Podcast.